Hello guys, so today we will discuss what is heap sort. Okay, wow, and I will show you how to code it as well and what it is. Okay, both we will do today. So heap sort is a comparison based sorting technique. Every sorting technique, most of the sorting techniques are comparison based. Okay, because there is comparison in them based on binary heap data structure. There are apart from comparison, there is counting sort also, which does not compare, but it simply counts in a frequency array. So this one is a comparison one. Now it is similar to selection sort, where we first find the minimum element and place the minimum element at the beginning. What do we do in a selection sort? If I have this array 1 6 7 9 5 4, what do we do? We find the smallest element in the complete array first, 1, and we exchange it. This is what happens in a selection sort. Then we search in this the minimum one, it's already there, so then we search from here to here. Then 4 will come at this place, 6 will go there. So that's how selection sort works. Similarly in this as well, we will do something like this. Okay, now what it is saying, we repeat the same process for the remaining elements, right? Now what is a binary heap? Okay, for heap sort, first we need to understand what is a binary heap. What simple definition is, binary heap is a tree which can have no child. These are called childs. This is the root, this is the root, and these are the child, which can have either no root or one or two child. Just one or two, not more than that. Okay. Yeah, no root is also tree, but I had to mention no child means 0, 1 or 2 child. Okay. Okay, so just remove this. So this is a binary tree, simple binary tree. Okay, in which every level except possibly the last is now here they are talking about a complete binary tree. A complete binary is the one which has on the last is completely filled and all nodes are as far left as possible on the left. A binary heap is a complete binary tree where items are sorted in special order such that the value in parent node is greater or smaller than the value in its two children nodes. What does it mean? The value in the first node is either greater or smaller than the complete tree below it. So here 1 is less than 2 and 3. So if there are some more elements like 5, 6, 7, 9, so the parent is greater than the complete subtree which is below it. Okay, and yeah, okay, so let's talk about what is the max heap here. Max heap is, and the later is called mini. The heap can be represented by a binary tree or array. Okay, so a max heap is the one in which the topmost element is the greatest of the underlying elements. Okay, 7, 8. Now below 8, 9 is not possible because each node, it applies to on each node, should have a greater element than the complete subtree, the left subtree and the right subtree both. So here only elements less than 8 are possible. You can put 7, you can put here 6. This is also by max heap. And here all elements less than 7, only elements less than 7. 1 can come, 1 can take 0 for 7, 5, 4. It's just an example. And similarly you might have judged what will be for a minimum heap. The topmost element should be the minimum. You can take any, like maybe this is 10, so the below elements on the left and right subtree should have values less than 10. So this will be 9, this can take 8, this can take 5, 4, but not 10, right? 8 can take maybe 1, maybe 3, Okay, now 3 can take what all? Less than 3. All the values less than 3 will be in its subtree. Okay, less than 3. Okay, now let's go ahead. Why array based representation? Yeah, as they said mentioned that the heap can be represented by a binary tree or array, but we will use here a array based representation for binary heap. So why an array based representation? Because see, simply I will draw a tree here. Okay, let's put some values in this. 0 1, we are just numbering it as of now, not some heap. 6 7 8 9 10. Okay, this much is enough. Now we will look at the array. If I make an array, what if I say, let's mark the indexes first. 0 1 2 3 4 5 6 7 8 9. Okay, just you can take 10 as well, but more than that we will need. Why? I will show you why that is required. So okay, if I say it's 0 here, let's put 0 on the 0th element. See here, now it has left subchild as 1, right subchild as 2. Okay, I see we can put it here. So we can make a relationship that 0's left subchild is 2 into I plus 1. It satisfies this. Okay, so this is I have put up. Now for this, for the right hand, it seems I can take up 2 into I plus 2 for the right one, right? So 2. Now for 1, 2i plus 1 will be 3. So here it will be 3. For 1, right hands 4, 2i plus 2. 2 into 1 plus 2 will be 4. So 4. Now for 2, 2 into 2 plus 1, 5. 5. 2 into 2 plus 2, 6. 6. Now let's go one by one. I have done for 2, for 1, for 0. Now 3. 3 into 2, 6 plus 1, 7. 7. 3 into 2 plus 2, 8. Now let's go for 4. 4 into 2 plus 1, 9. 4 into 2 plus 2, 10. Right? So this tree can be simply represented by an array. So why to go for a tree structure? Like for to write a code for a tree, we need the first we need to mention the nodes, the structure for the nodes. Then we need to code it, right? So when we can store it in in an array, why we should go for a tree? There's no reason. Okay, so we will represent it as a tree. Since a binary heap is a complete binary tree, and yeah, remember this, it is a complete binary tree. Okay, complete binary tree. By complete binary tree, what is it means? That in the tree only one node is possible. Two nodes are also possible. But this case will not be there. If there is a left child, there will be a right child as well, or there will be no child at all. This has no child, this row. Okay. So what will be the benefit to us if we use a complete binary tree? Why this applies to complete binary tree? Understand that as well. Because if, see here, in this example, if you take on 5, say it's 11 and there is no left right child. Okay, So after 10, let's make the array here. There will be 11, 12, 13, 14. Okay. Now if I go for 5, after 4 I will go for 5, right? 5 left side is 11. 5 into 2 plus 1, 11. But there's no right child, and if I go for this code, it will surely go for a right child, which will give us 12, which I don't need, because if I reached 5, I need either a left child or a right child, but there's no child. So we just use a complete binary tree for heap sort. Let's go ahead what it says. If the parent node is starting at index 1, I, the left child can be calculated by 2i plus 1 and the right child by 2i plus 2, assuming the indexing starts at 0. Remember this. This only works for indexing start at 0. If indexing starts by 1, okay. If indexing starts at 1, this will be 2, this will be 3. Now, you can calculate it easily. It will be 2 into I, the left one, if someone does by that. And the right one will be what? 2 into I plus 1. So, it can be easily figured out. Depends on from where you start your array, from 0 or from 1. Okay, let's go ahead. Heap sort algorithm for sorting in increasing order. Okay, at this point the largest item is stored at the root of the heap. So largest item is stored, what it means, it is a max heap. Replace it with the last item of the heap followed by reducing the size of heap by 1. Okay, finally heapify the root of the tree. We will see what it is. Repeat step 2 while the size of the heap is greater than 1. How to build the heap. Heapify procedure can be applied to a node only if its children nodes are heapified. Must be performed in the bottom of order. Let's understand with it. Ignore this, I will make you understand with the help of example. It's easiest. Okay, so first of all, input data. In input data it says input is 4. 4 is the greatest element. I have to do nothing. Then 10, I will insert as a left child as 10. Now what will I check? So let's see here. Applying Heapify to procedure to index 1. So what it did is it first created an array. Okay, so we also create the array 4, 10, 3, 5, 1. Okay, this is a complete binary tree. All can see. Okay then. Now for the root element, applying heapify procedure to index 1. For heapify, what it will be do? Replace it with the last item of the heap followed by reducing the size of the heap by 1. Okay, it is not explained. We'll look from here. Increasing order. At this point, it is stored at the root of the heap. But this is not. Last item of the heap followed by reducing the size of the heap by 1. Finally, heapify the root of the tree. Step 2, while the size of the heap is greater than 1. Let's see it like this. Okay, 4 is the smallest element. No. Here it needs to be the greatest element. We will check. Or this insertion is wrong. We can delete this. Let's try some other way. Okay, I will just, this is for explaining. Okay, I had 4. I inserted it. Next is 10. I inserted it here, but then I searched. 10 is greater than 4. Go back. I did it. Next is 3. I inserted it. It is at its perfect place. I have to do nothing. Next is 5. I checked. 5 is greater than 4. Replace them. Okay, wait a second. Replace them. Here it will be 5. Here it will be 4. Okay. Now it will check by 10. No, it's less than that. Ignore it. Next is 1. I will insert it here. 1 is already less than 5, so I don't have to do the. So this is a heap. Max heap because the topmost element will have 10. Okay. Now let's go for the coding part. Okay. See here. Okay, wait a second, guys. We need a second screen for this. So I will code along now and you can understand it. Excellent. Okay, so I will code on idea. So best site that I like to code on. So first of all, let's change this to bit slash std c++.h so we don't have problem. Okay, okay, so let's take an array which we will sort. Simple array might work. So something like this. Okay, and take the array size as well, like it's written here. Size of array arr divided by size of arr 0. So this will give us the size, and we will call it is second. It's been using. So and we can call heap sort arr comma n, the size of the array. Okay. Now we will write the functions. So see, this is the heap sort function. We will first write the heap sort function. I will explain along with. Okay. Heap sort int arr comma int n. So now build heap rearrange array. Okay. So this first step is to build the heap. So let's discuss about Heapify first. Then void Heapify int arr comma int n comma int I. Okay. So now see what it is trying to do. Okay. So to heapify a subtree rooted with node I, which is an index in ARR and is size of the heap. This function it has taken to do what? Let's see. If this is a tree 1, 2, 3, 4, 5, 6, 7, and an array it will be 1, 2, 3, 4, 5, 6, 7. Okay, guys. Now it is saying we need to heapify a subtree. Say like this. We need to heapify this with node I 0, 1, 2, 3, 4, 5, 6. This is the first node. So node 1. This is the index, okay, which I need to heapify, right? So what have they done? Int largest equal to I. So the first element they have taken initialize largest as root. So I will take LG as the largest one. Okay. So LG I have taken as I, which is my index. Fine. I took 2 as the, so here the value is 2. This is just for signifying that the value is 2 in LG. Now, and the left node will be what? 2i plus 1 because it is starting from 0 indexing, and right will be 2i plus 2. Similarly, now I have the left and right value. Now if the left child is larger than the root, we need to check. Now suppose this is larger than the root, what do we need? We just we will just say that the lg is equal to that element L, because left is larger. But we search that is the right element greater than the root. Now remember, it is not searching for the root, we are searching from the largest. That which one of these, 4 or 5, which one is greater? Okay, we are searching for that as well. See, the first step did largest is equal to 4. Let's clean this up. What has this done? Okay, see, first it said we will take largest as 2. Okay, now if the left element is greater, 4 is greater than 2, right? So we said, sorry, it is storing the index, so lg is equal to 1. Index of 2 is what? 1, right? If lg is, now lg will be what? 4, 3, and ARR of lg will be 4, right? Now it will check for the right element. Right element 5 is greater than ARR of lg. It is 4. It's greater than that. So lg will replace to which value? 4. Index of 5 is 4. Index of value 5 is 4. lg is now 4. Now in the last, we need to replace this with the value, right? So what it will do? It will just say replace 2 with the index which has value more than me and more than the other child as well. So it will get replaced. Now it will be 1, 5, 4, 2, and see, this one is completely heapified. Now if you go to the next, this will search for just these two. Like this it will be, and see, it has recursively heapified the affected subtree. It does not stop there. It says if for the largest one, for 5, again do the heapify process. Wait a second. Largest is not equal to root, it will swap. Largest is this one, 5, not root. Yeah, it means I. Swap it with I. So here 2 will be here, 5 will be here, and this is the largest. So it will say heapify ARR, comma n, comma the index of the largest. Heapify this again. Okay, so why it is doing this? So that these two are also heapified. What if it gives us a greater value and let's say here it is 3. So for that reason it has said to heapify this again. Okay, not this. Actually the largest is this one, right? The largest has index of this 4, has index 4. Now 2 will be here, present here, so it needs to say that heapify this affected subtree. Okay, so now we will code this. Okay, and we will code and see, let's see, for check for heap sort also, what it has done in heap sort. It said build the heap. To how to build the heap? Okay, let's discuss this, how it is building the heap. See this, there are some values, while values, take 10, 5, 9, 8, 7, 6, 4. Okay, 0, 1, 2, 3, 4, 5, 6. Okay, so now what we need to do, this is a, and how will this look like? 10, 5, 9, 8, 7, 6, 4, right? Now we, from where we need to start heapification process. Okay, here it's of no use on the leaves, it's of no use at all. Okay, and how many leaves will be there? It is a complete tree. Okay, so we can say that if it's a complete tree, it can either have 3 or it can either have 4, but it will be less than n by 2 because the last node will have the leaves are will have most of the place. You can think about it. Okay, now so from where should we start? N by 2 minus 1. Either it will take this or this. If it has n here and it's 7. Okay, right, it's 7, right? Yeah, so 7 by 2 will be 3.5 minus 1, it will be 2.5. So I is equal to, for 2.5 it will take 2, so it will start from 9. So simply it will start from the 9 from index 2. From here it will start the heapification process, and it will check for it. Is it greater? It is greater, it will do nothing. This is the largest one. Then for this one 5, it will just move back. For 5 it will do the heapification process, it will see it's greater than 8, so it will remove this and replace it. Here it will be 8, here it will be 5. Okay, and then it will go for heapification. Here, like recursively heapify the affected subtree, it will heapify this as well, but it will remove the same. It matters when it's a big tree. Okay, and then it will heapify 10 as it is greater than both. It will do nothing because it is greater than the below elements. So this is the simple heap sort. It is the very basic one and easiest to write. I say that it's the easiest to write. Okay, so now let's code this. Okay, okay guys, now let's code this. So first we need to write the heapify process. Okay, so what did we did to heapify at a node I, and this, remember, this is a max heap. Okay, so to heapify, first we need to take the largest. Say largest is at index I, and say left one is 2 into I plus 1. Same for right one, it's 2 into I plus 2, as I said. Okay, now what do I need to do? I need to check if the if it's a max heap, so I will check for the left one if the left one is greater than the largest one, because then only it needs to change, right? It is greater than the largest one. What do I need to do? It's a single line, so I will not write this. I will just say give largest is equal to L, right? Largest is equal to L. And remember that there may be a problem if I am at the last element. Maybe someone say heapify the last element. So what it will do? It will go look for like here. It will go look for 6. 6 and left will be 6 into 2 plus 1, 12 plus 1, 13. Right? Now this might create a problem. Why? Because ARR in the array there are only 7 and the index is only till 6. How can we access the index out of, it will show index out of bounds error. So to check this, we can simply put here that L is less than N and N. What this will do is, if before, in AND, if any one of the condition is false, it will not execute. So if here the first condition is false, it will not check, go for the second one, and we will be safe. Okay, now for the right one, if r is less than n and then ARR of r is greater than an ARR of largest, what we need to do. Largest equal to right. And now what we did, if it is done, we need to heapify this part as well, right? The subtree. So to heapify that, what we will do, we will simply call heapify. But remember, heapify is only required, first we have to replace it. Heapify is only required if the largest is not equal to the original one, which was I. We first need to swap the values, ARR of largest, comma, ARR of I. And then we need to heapify it as well. Heapify ARR, comma, N, comma, the affected subtree. The index will be what? This one, the 4, which was the largest, which got replaced by here 1. So this will heapify. Now the heapify process is done. Now we need to heap sort. So for heap sort, what we need to do? First, we need to create the max heap. For max heap, I showed you how to do that. It will start from n by 2 minus 1. There will be no problem if you start from n. Just it will take more number of operations. Remember that. I is greater than equal to 0, I minus minus. Okay. Just do heapify ARR, comma, N, comma, I. Now, heapification process is done. We have a max heap. Now we need the array. The main but for what we did max heap was to acquire an array, right? Now listen to me very carefully. How we can acquire an array out of this? Okay, so let's take this like this. So I have an array, max heap. I will draw max heap. 10 is here, 9 is here, 8 or 4 or 3 or 0. Okay, like this. Here we can do 2. Now this will be heap sorted and 2 will be here and 0 will be here. It doesn't matter at all. So this will be our array 10, 9, 8, 4, 3, 2, 0. See, I need an I need an in increasing order. I need an array in increasing order. What I'm going to do, I will say, okay, you need an array in increasing order. No problem. What I will do is one by one extract the element from the heap. How? I needed this, right? What I will do is I will say take this out 10, okay, and place it. What I need is wait a second in increasing order, so I will need the smallest value first. Or the greatest values. I cannot take a smallest. I have the greatest. So I can place the greatest at the end. So simply what I will do is I will say replace this 0. Okay. 3, 2, 10. Now 10 is at the right position. Now what I can do is I will say heapify this. So let's see this very carefully. This is a very amazing process. I will say 4, 3, and here's 2 now. Okay, I will say heapify this. What this will check? It will check I am less than this, I am less than 8. So it will replace 9 because 9 is greater than 8 as well. So it will come here and 9 will be here. Now what it does, it goes for a heap sort on the affected subtree. It will go for a heap sort on this subtree. It will check 0 is greater than 4 and 3. For 4 it will replace, so what it will do is, here it will be 0, here it will be 4. Now the greatest element is 9, so the new array, in the new array 9 will be here, right? Wait a second, guys. So you guys have a thought about this. 9 will be present there, okay? Okay, so yeah, what I was saying. So currently 0 was here, 9 is here, but now the structure looks like 9, 4, 8, 0, 3, 2. Now what will I do is I will replace, this is fixed, so what I will do is I will replace this with 2, 2, 9. Can you see? This will get us, this is like a opposite of a selection sort. What I am doing is I am placing the greatest element at the last. In selection sort we place it at the first if we are going for a decreasing order, right? So now let's code this. Okay, so in coding what we are doing, we are starting from the yeah, we have the, so we will start from the last index, last will be n minus 1, right? So n minus 1 comma I is greater than equal to the last element. We don't need to go I greater than 1, greater than equal to 1 will work, okay? Because the last first element is already, will be already sorted, I minus minus. Now int I, now what we need to do, I am doing a swap and I am placing the, uh, ith element which I have with the first element, because first is the greatest element, okay, and I will place it on the last. And then what I need to do is I will just heapify arr comma n comma what I did placed the first element I needed to be set, right? 0. From 0 it will heapify because I need to the greatest element to be set. And this is done, and we can, heap sort is done here, and what we can do is we can print this array int I is equal to 0, I is less than n, I plus plus c out arr of I space. Okay then guys, let's try this out. Run. Oh, we have some errors. They see, now we encountered an error. Read this very carefully. In function void heap sort, it tells you everything. Okay, error expected semicolon before greater than equal to or greater than equal to. As it checks for the operators, so it will say not before I greater than equal to, and it has mentioned the line number as well. Check this 22. In 22 there's a there's a comma, but it needs a semicolon. So we will go for edit line number 22, and here it is semicolon. Now so you should be able to read the errors as well. So can you see this? Okay, this is opposite of what we required. We were thinking 62 will be on the end, right? So what happened? Can we check that? What happened with it? Why we swapped the greatest element error of 0 to the last element error n minus 1, right? And we did the Heapify process. But what it did, see this is wrong. Heapify took the complete array. It included 10 as well, but I did not need it. It included 10 as well to Heapify, right? And if it includes 10, then 10 will again come to the front. And but on n minus, now n index is going to decrease. On I, yeah, I will be n minus 2, and for n minus 2 it will do. So this is the main point here. We need to heapify only the first n minus 1 elements, not the last element. Okay, so this was a mistake. We need to check it. See, again there's some mistake being done by me. See, okay. Okay, let's see it. But we are doing wrong here. N minus 1. Okay, again wrong. Because it's only for once that we need n minus 1 elements. But the next time it will be n minus 2 and the decreasing. So it will be I, not n minus 1, right? It was only for one case I took it. So see, after a lot of trial and errors, it's right now. Okay. So now I guess no one will have problem and can write this code on their own. Similarly for min heap as well, what we need to do, we just need to change these arrows because it would be the smallest element. Okay, it will be the smallest element. We can do changes here only. See this. It will be the smallest element on the top, and this needs to be the less than then. This needs to be the smallest element. This will also change. Let's copy this. And if the smallest is not less equal to, we will replace it and we will heapify the rest of the subtree, right? In heap sort, we will heapify is always required, but check this out. It will just give the opposite of what we have now, right? Why? Because here it was a min heap, and in the min heap, what it did, it took the first element and replaced it to the on the last, and then subsequently, okay, so 0 had the minimum element 3. So this is this. Now we implemented a min heap and we did it. Okay, so okay then guys, I will be again back with some other topic or coding question. Okay, bye bye.